Hi, Rohit. We'll just wait for 1 minute and then we'll start. Rohit, you can see my screen, right? And that I'm writing.
Yes, I can see it.
Okay, then let's give it a start. Uh, I think what we're going to do today is that we will go through just a moment. 1 minute. Yeah. So we will go through one technique which is known as Xgboost. Okay. So we will look into the boosting algorithms now. We have looked into bagging algorithms earlier. If you remember, we looked into the random forest algorithm, which is one of the bagging algorithms, right? So in that case, we learned how that algorithm specifically is helping us to do things. And now we are going to look into an algorithm of type boosting, right? So this is also an ensemble kind of a method, right? But this is a different way in which we do things. So the name of this is Xgboost. Okay. Now there is a meaning or there is a reason why it's called Xgboost. Maybe you have already heard about this. So XG stands for extreme gradient. Okay. XG stands for extreme gradient and boost stands for boosting. Okay. So that's the reason why it's called Xgboost. Now we have to first understand what is boosting. If we understand how boosting works, then we will be able to understand how we are going to do this extreme and gradient things. So boosting, just like bagging. So in case of the ensemble methods, which we were looking into earlier, right? So we looked into bagging methods. So that is one method. And the other method is known as boosting method. Now, just to set the stage, these are called the ensemble methods because what they are doing is they are stacking up, or they are stacking is actually a wrong word to be used here, but they are doing some kind of, let's say, uh, team work, we can say, right? So they are doing some kind of teamwork within themselves so that they can solve the machine learning problem which we are going to throw at them. So rather than using one model, or rather than we trying out n number of models, they are trying out n number of models in themselves, and then they are giving us some results. For example, in case of bagging, we have looked into random forest. Okay. So in case of random forests, there were n underscore estimators, if you remember, which is by default, let's say, equal to 100. What this means is if I fit a random forest, and the reason why it is called mighty is because it's going to fit 100 decision trees, right? And then it is going to take the average. Okay, it is going to take the average of the findings, right? Or if I am going to call this, let's call it in a different way. So I'm just going to average of, let me just remove this. So I'm going to call it the average of all these trees power, right? So it is going to take the power of all the 100 trees and it is going to take an average of that power, right? Which means that rather than having one tree or let's say 5 trees or 10 trees, I can have 100 trees which are actually created in parallel, right? Which are actually created in parallel when we looked into random forest, which is a bagging method. And we were able to, in parallel, train 100 trees. And 100 trees, after they were trained, we took the average of their power and we concluded what each and every row R1, R2 until R of n, if I consider R is just a part of, let's say, n dimensional data, or a data which has n number of rows, right? So for each and every row, we are going to get the y hat. So y1 hat, y2 hat, y3 hat, so on and so forth until yn hat, right? So this method was really powerful because we were combining the power of n number of trees. And the same thing is going to happen into boosting also, but in a slightly different way, right? So what we do in case of boosting, okay, what we do in case of boosting is that rather than doing things into parallel, what we do is we start with any weak decision maker. Okay. So what I mean by this is, let's take a decision tree. Xgboost usually is going to take a decision tree in the backend. So let's take an example that I've fit a decision tree. It is weak. Okay, I've not tuned it. I've not really done anything with this. All right. So let's say this is my model M1. Post which, what I do is that I give this model my training sample, or I give this model my training data. Using this, I have trained this model, the first model, which I'm calling a weak decision tree. You will get to know why it is called a weak one. It is weak because I have not tuned it. I have not done anything special to make it strong. I have not done really anything to make it strong. It's just out of box decision tree. Once it is trained, this is the first classifier. Let's say, just for the sake of simplicity, we are doing a classification kind of a problem, and let's say it is a binary class classification problem where either the answer is going to be true or it is going to be false. Okay, now in the first tree, it is kind of a weak tree. Let's not go into the metrics which I'm trying to use to say whether it is a weak tree or a very highly performant tree, but let's say that it is just a weak tree. And then what I'm going to do is that I'm going to take its results, okay, or I'm going to take its performance, okay, in terms of what I'm going to define as weights, right? I'm going to explain how these weights are taken and so on and so forth. But just as of now, imagine that these weights are, let's say there is a student S1 and he's appearing for exam E1. The feedback of exam E1, which he has taken on the 1st of March, is again another exam held on the 5th of March, where the same student is appearing for the next exam, exam 2, which is of the same subject. Let's say it is for maths, right? And he's appearing for the same exam and he's trying to prepare for the board exams, let's say, or the 10th exams or the 12th exams. Now, whatever feedback, whatever learning we have from exam 1 is being fed as part of its learning in form of weights, okay, in form of weights before he appears for the next exam, which is on the 5th. Again, on the 10th, I'm going to take the same student. Okay, I'm going to take the same student and take another exam E3. While the student appears for exam E3, I'm going to take the feedback of E2 as to how good or how bad he was. So let's say he was very good in algebra, right? But he was not good in calculus, right? He was making some silly mistakes when it came to geometry and so on and so forth. So whatever was good or bad, I took this kind of a feedback and I have sent that feedback over to my student. And over a period of time, what is going to happen is, after every 5 days, you see, after every 5 days, the same student is appearing for different versions of the same exam of the same subject here. In this way, in this sequential order, okay, in this sequential order, I'm trying to improve what is going to be the final performance of my students. So let's say this was in the month of March, let's say. By the time it is April or May, This person may have already given, let's say, 50 exams. So by the time this person is sitting at exam 50, which is just the 50th mock test, you can say, for maths for class 10 board exams, 10th or 12th board exams. By this time, he has got at least 49 feedbacks, right? From the previous 49 exams that he has given, he has got all the 49 feedbacks. And basis that 49 feedbacks, his intention will be to improve the areas where he is not doing good. So that by the time he is E50, by the time he has reached this stage, he should be quite good. I'm not going to say he's going to be the best. He may not be the best, but he's going to be really good. He's going to be quite good when it came to all the subjects or all the chapters which are there in math, right? Which will be there in the 10th board examination, right? So I'll use the same concept, right? I will use the same concept to train my decision trees also, right? So what I'm going to do, I'm just going to create my first model and I'm going to give it my training data. Let's say this is my first model and I have given it my training data, right? Post which I take the weights, or otherwise I'm also going to call it as a weighted sample, right? I'm going to call it as a weighted sample. We're going to define this term, so don't worry right now. And using this weighted sample, I'm going to train the second classifier. And then using the feedback, I'm going to train the third classifier. Using this feedback, I'm going to train the fourth classifier. Until and unless I have reached a stage where I have at least created m number of classifiers. In my example of the student, there was only one student, right? But here what I'm doing, you can say that these are different models, or in one way, it is actually the same model which is getting updated into different versions. The M1 is being improved to M2 because in the second run, I have taken the feedback from the first run. And then by the time it has reached M3, which is the third version of the same model, M, right, it has improved a little bit. And then from M3 to M4, it has improved a little bit until it has reached something like 100 or 200 or 300 iterations that we have done. So until we have done these kind of m number of iterations for the same model, we have improved it. You can also imagine this has to be something like this. So let's say you are creating a model M1, which is your first model, and then you do some kind of, let's say, hyperparameter tuning, and you create M2, right, which is your second model, right? Then again, you do some kind of a hyperparameter tuning. You find something, and then you do some changes, right? Then you create model number 3, which is your third model, right? Then let's say you identify you have done something wrong with the scaling. Let's scale the data, and now you create model number 4, which is going to be the fourth model, and so on and so forth. So in this way, let's say you have reached a place where you have created the 100th model. However, the type of the model here is a constant. Let's say you started with a decision tree. Model 1 is also a decision tree. Model 2 is also a decision tree. It's not that after 4 models or 7 models you decided, no, let's scrap decision tree, let's go to random forest. No, for all of the 100 models, it is actually the same type of model, right? By the time you have reached 100th model, you can be quite sure that you have done a lot of tuning on top of the model. Hence, the model is really a good decision maker, right? The model is really good a decision maker, right? Now, what are these weights? And what are we exactly doing in each and every of these stages? Because as you can understand, this entire scheme of things that we are running over here, right, it is not actually running in parallel. It is actually a sequential kind of an operation, right? So it is not that what we saw into bagging, right? In case of bagging, or let's say specifically in case of random forests, we saw that if n underscore estimator was equal to 100, I was actually training all the 100 trees into parallel. But here we are not doing it. We are doing it one after the other. So M1 followed by M2, followed by M3, until I reach, let's say, M500, right? This may raise a concern related to uh, the computational capability, or the kind of, the computational power that we are going to need, right? But we are going to handle that at a later stage, right? But the only two questions which we have over here, or which we should have over here, is that what are these weights, or how am I going to calculate these weights, and how am I going to execute these stages? So which basically means I need to know the exact algorithm. If I know the algorithm, then I should be able to code it and then I should be able to run it, right? Until this point in time, do you have any doubts?
No doubts as of now.
Good. Okay. Just 1 minute. Okay. So what I'm going to do is that before I come to the weights or to the weights, I'm going to define something which is known as the objective. Okay, the objective, or I can also say the final objective. The final objective of what I would like to do in case of any kind of boosting or something like Xgboost. We are also going to look into other boosting techniques like Adaboost, okay, gradient boosting, and so on, right? And then we'll come to Xgboost because there is a logical flow, there is a logical order in which they, right? But in any case, the final objective is really very, very simple. Let me call that as OBJ. My final objective is L plus this omega. Okay, so this L is basically a loss function. I have to define some function by means of which I need to do a calculation. I'm going to tell you what this calculation is going to be. And then the sigma sign is basically an operation. Okay. Let's try to understand what this really means. If I'm going to create m number of models, one after the other, one after the other, one after the other, and finally I reach, let's say, the 500th model, how am I going to ensure until what time, right? Until what time should I continue creating the models? Or in other words, how can I be sure that the 500th model that I have created is the best model out of the lot, right? Best of the lot. How do we know that? The easiest way to know that is that for each and every model, right? For each and every model, I can find out what is my error, right? What is going to be my error? So for example, if this is a classification problem, and let's say just for the sake of simplicity, I have a balanced data, right? I have two classes, class A and class B. Both of them have 200 samples in my data, right? It's a very, very balanced kind of a data. Either any observation Ri is going to be of class A or of class B. If this is the case, we don't know anything about the distribution of the data. Okay, we don't know whether they are linearly separable or not, or whether they are easily differentiable and not, and so on. But if let's say there is any row R1, or let's say I have 400 rows, right? So the total number of rows in my data is equal to 400. Out of 400, how many have I correctly classified in the first model? Let's say I've classified only 135, right? So this gives me what is the accuracy of my model. Or if I reverse this, this is going to give me the loss of my model, or this model, how much error it contains, right? So that is the definition of loss. Loss is how much is the error, right, in each and every model. Now that from M1 to M2, when I'm going to use something known as a weight. I don't know what this weight is or how it's really going to be calculated, right? But as of now, I'm going to consider this weight W1 is equal to some kind of a feedback, as we have already defined. So for each and every model, I'm going to define one weight, W1, W2, W3, W4, and so on and so forth. So these are belonging to the previous models that we have created, right? And then they are passed on to the next model so that M2 can be an improvement over M1, M3 can be an improvement over M2, and so on and so forth. Now, as we are increasing, the objective should be that the loss should be decreasing, right? If by the 500th model, I am at a position where, let's say, I have gone to a position where 390 out of 400 I have classified exactly correctly, then I can say it is a pretty good model. After I have done a fit of 500 models, let's say 390 points are correctly identified out of 400, right? So over a period of time, the number of misclassified points right? The number of misclassified points have decreased, which means the losses have also decreased. So the objective, okay, the objective of any boosting kind of an algorithm which we are going to see, irrespective of what it really is going to be, I'm going to have some loss which is defined by L, and then I'm going to do some regularization defined by the word sigma. And my objective is over a period of time, I'm going to regularize my model in certain way. This is the regularizer. Okay, I'm going to tell you what is the regularizer. This is my regularizer, or it is in my student and exam example, it is my teacher, or it is my invigilator, okay, who is, or is the person who is giving me the feedback, right? And he is giving me the feedback in such a way that over a period of time, my loss value has to decrease. So basically, this is also known as a minimization problem in case of, let's say, computer science. So we are going to have a minimization problem where my objective is to minimize the losses by means of this regularizer that I'm using, right? That's all I'll have to do. If I'm able to do that properly, then by my mth model that I have created at the end of the sequence, I should have a very, very small loss. My loss should be very, very negligible, right? Now, keeping this in mind, let's look into what all are, let's say, the types of boosting that we can do. We'll start with a very, very simple kind of a boosting. This is known as Adaboost, right? So the first boosting algorithm that we are going to look into is known as Adaboost. Why is it called Adaboost? Because this term ADA refers to adaptive, and boost refers to boosting, because we are going to do boosting operation, right? Why is it adaptive? And still we have that outstanding question as to what are weights really. These both of them are going to be clear now, right? But at least we had two questions initially. What are weights and what are the steps? So let me answer question number two. Question number one will be immediately answered. The first question is, let's say, just to set up the environment, okay, let's do some kind of, it's a terminology setting. So let's say capital N is my number of samples in my data, right? And over a period of time, m number of iterations were done, and hence m number of trees were created. As I told you, in any boosting kind of a scenario, the learners, or in each and every iteration, what we known as the weak learner is otherwise a decision tree. So let's say I have created m number of decision trees, right? My class outcome is binary. Okay, my class outcome is basically binary. It is given by the variable y, which can either be -1 or +1. So these are the two class values that I can have. Either it is -1 or +1. Now, keeping this in mind, what I'm going to do, I'm going to define an initial model, all right? And before I even create an initial model, I'm going to create an initial value of weight. This weight is going to be just a random number. Okay, it is going to be a random number. Just consider this as a random property which will be attached to this model, the first model, very soon. The first weight will be initialized as 1 divided by n, right? So it will be done as 1 divided by n. So for example, if I had 400 samples as per my last example, right? If I had 400 samples, and the initial weight is going to be 1 divided by 400, you can do the math, you can find the value. Now, what I'm going to do for each model m of I, let's say small m of I, in the range of m, right? So I will be created m number of trees, right? So let me just remove this from here. Let me try to write it over here. Let me take another pen. For each model in the set of m models which I have to create, the first step which I'm going to do, fit my first model. Let's say my first model is called gm of x. So x is my input and g of m is my model, right? And I'm going to take the weights as an input over here. How am I going to take the weights? I'm going to tell you. So I've already defined an initial value of weights, which is 1 divided by n. I'm going to somehow use this weights value while I'm doing the modeling thing. How? When I'm done creating the model, when I'm done fitting the decision tree, I'll calculate two things. The first thing is going to be my error, right? And this error is going to be nothing but the loss. So what I'm going to do, summation I equal to 1 to capital N. So for each and every observation in the data, multiply my initial weight, right? Multiply my initial weight with a function, right? With a function I, where I is going to check if my expected value for that row did not match with the value provided by my model for that row. So this function I is basically my invigilator. He's checking which questions have I answered, let's say, correctly or incorrectly. So for each yi, which is my actual value, it is trying to predict, or it is trying to see if that actual value matches the expected value or not. And I also divide this entire thing by summation of I equal to 1 to n of the weights. Now the thing is, if I have already created one weight, then how do I iterate the values of weight? So here what I'm doing is, when I'm creating each and every model, right, the number of weights will also change, right? Because I will be equal to 1, 2, 3 until n, right? So it is also going to change. So if I is equal to 1, my weight is going to be 1 by 1. I is going to be 2, my weight is going to be 1 by 2. When I'm starting off, it will be 1 by n and so on and so forth. Initial observation of the weight is going to be 1 by n, right? And then I'm also going to make a change in the weight. Now, how do I make a change in the weight is something which I'm going to talk about, right? But as of now, my initial value, okay, my initial value of the weights is going to be 1 by n, which is going to be a random number because I don't have any control on n, right? Basis my use case, n can be anything, right? So let me remove this from here. And then what I'm going to do, this is step number 2. So step number 1, I've created my model. Step number 2, I calculated the error. Step number 3 is that I'm just continuing from here. Okay, I'm just continuing from here over here. Step number 3 is going to be, I'm going to calculate something which is known as alpha of my model M. So each model can be given as M, let's say. I'm just calculating something known as alpha. And alpha, I'm going to define this as half of 1 by 2 of log of 1 minus ERR of that model M, okay, divided by ERR M, right? Why I'm doing this is because I'm taking a logarithm of 1 minus error divided by error, right, which is representative of how much log of error or log loss, okay, how much log loss I have for that specific model M. So let's say I am at model M1. So what is the log loss, or what is the logarithmic value of the loss created when I have created model number M1? And then I'm also halving it, because halving is actually going to penalize it. This is actually provable by means of, it's a calculus, that if you can actually do a half, and that approximation is going to be much more closer. So for each and every model, I got the error, and from that error, I calculated another value alpha of M, right? Using these two values, I'm going to do the fourth step, which is going to be change in the weights. I have to update the weights also, right? Because if I don't update the weights, my initial uh, assumption is going to be validated. So if I have one model and then I'm creating the next model, I have to use this weight. So the initial weight I have set as 1 by n. What is going to be the next weight? I'm going to create another model n3. What is going to be the next weight? So I need to know the next value of the weight, right? I'll have to change this because this is my feedback. If if my student has given that first exam on one day, then while preparing for the same student preparing for the second exam, I need to give him some feedback, and that feedback will change, right? The feedback cannot be same for all the 500 exams, right? After giving 500 exams, how can you be still weaker into calculus, right? It is a very, very less chance. So the weight has to change. How do I change my weight? Is that I'm just going to take the new weight. Let me just remove this. Let me remove this and let me write it in a different way. The new weight or the next weight, the new weight is going to be equal to or assigned by a value old weight, right, multiplied by exponent of, okay, exponent of alpha m, which I have calculated here, alpha m multiplied by that I function. I function is doing what? It is checking if my expected value matches or does not match with my model's outcome, right? So I'm simply taking an exponentiation. I'm taking an exponentiation of my alpha m, which is basically my log loss representation, and I'm multiplying it with a function I. I have no name for I. I have no name for alpha here. It can be named anything. And this function is basically telling me how good or how bad I am, which I'm multiplying with the log loss for each and every I. So because this is uh, the iteration is within the models, right? The iteration is within the models. For each and every observation, I'm going to repeat this. Right. So for each and every model, I'm going to repeat this. I'm going to continue to do this for each and every model. I'm sorry. Yeah. Now, when I've got the new weights, these weights that I have calculated will be for each and every row, where row can be represented as I equal to row number 1, I equal to row number 2, I equal to row number 3, and row number n. So for n number of rows, for each and every row, I'm going to give a weight, right? And then I'm going to normalize it. The reason why I am normalizing it is because it can go beyond a certain value and I need to scale it. If I don't scale it, then I will not be able to track its changes properly. I have to scale it so that I can fit it into some kind of a distribution, right? And that is exactly what I'm doing, right? Let me quickly repeat. In the first stage, let me clear the drawing. In the first stage is that for each and every model, for no, let me just clear the drawings. Weights Wi is going to be 1 divided by n, where I is in the range of 1, 2, 3 until n, right? This is for each and every row, I'm going to get the weights, right? For each and every row using a formula like this, I'm going to get the weights. The initial value of the weights is going to be 1 by n. And then for each model m in the range of 1 to capital M, because M is the total number of the models which I have, I'm going to fit a model. This is step number 1. I'm going to fit a model which is GM of X. And then I'm going to get the error, right? Error of that model, which is given by what? Summation of I equal to 1 to n. For each and every row, I'm going to check what is the weight. And I'm going to check what is this cross checker function divided by Wi, or the summation of I equal to 1 to n Wi. Once I get the error, the third step is I calculate this alpha m value, which is basically giving me the log loss, half of log of 1 minus ERR m by ERR m. Once I have calculated this, the fourth step is going to be within this loop itself. This is going on. Within this loop only, for each and every observation I'm going to calculate the new weight. This is going to be the old weight multiplied by exponentiation of alpha of m multiplied by this I function. Just for the simplicity sake, I function I have not really entirely written, but I function is basically equal to yi not equal to gm of x, right? So it is basically looking at the errors that I'm making for each and every row. In this way, I have got the weights for each and every observation, which I'm going to normalize now. So outside the for loop, I'm going to do a normalization or a scaling of the weights, right? I'm going to scale all the weights, right? Once I have done that, I have now got the weights. I have now got the weights for each and every row. How do I do that? So let's say I have just 3 rows, right? Let's say have 3 rows, R1, R2, and R3. And W1 is the weight for R1, W2 is the weight for R2, W3 is the weight for R3. Now let's say W1 is equal to a dummy value. Okay, W1 is equal to, let's say, 1, W2 is equal to 2, W3 is equal to 3, let's say. So the total is what? 6. How do I normalize this? 1 by 6, 2 by 6, 3 by 6. Now this normalization has resulted everything to be within a probabilistic value, 0 to 1, right? Now that I have normalized it, I have got the normalized weight for each and every row. This is from the first iteration when I created model 1, or when I did one pass, when I did one model for all the n number of rows. For all of the n number of rows where n is equal to 3. In this case, I created one model and I've got the weights. Now I'm going to take these weights and I'm going to create the next tree, M2, and I'm going to repeat the entire process. Okay, I'm going to repeat this entire process. I'm going to repeat this entire cycle. And then I will get a next set of weights using which I'm going to use model 3, right? And then I'm going to get, let's say, model 4. I'm going to get, let's say, model 5 until I have done the iterations up to m number of models, right? That's the objective. We have already defined earlier that n is the number of rows in the data and m is the number of models, right? M is the number of models which we have. Once I have done that, okay, once I have done that, my final outcome is going to be what? My final objective is basis what kind of problem statement I have, basis what kind of problem statement I have, right? I'll have to find out what is the final model's status, because my objective is L plus omega, as much less as loss. This is the final objective. So the final model, right? The final model or the formula for the final model is going to be different if I have a classification problem or I have a regression problem. If I have a classification problem, right? If I have a classification kind of problem, then what I'm going to do, simply I can take a sigmoid, right? I can take a sigmoid of summation of small m equal to 1 to capital M, means all the models, alpha of m multiplied by what is my outcome, gm of x. Oh no, so, yeah, yes. So I'm going to take a sigmoid. Why a sigmoid? Because I have to compare all the trees and find the probabilistic outcome in this case. So my idea is I'm compare all the trees and find the class with most weights or the most weighted class, right? The most weighted class is what I'm going to find. Even if the models are created in a sequential way, if I take a sigmoid, I can do this by the nature of the function sigmoid. But if in case my problem statement is that of a regression, then what I'm going to do, I'm going to do an argmax. I'm going to do an argmax of summation m equal to 1 to capital M of alpha m multiplied by gm of x, where gm of x is my model, alpha m was the log loss which I have calculated out of my ERRM. In this case, it will be the regression, right? In case of the regression, what I'm doing, I'm simply taking the highest sum value. So I'm just taking the highest sum value in case I'm trying to predict a continuous variable. And in case I'm trying to do a classification, I'm just taking that class which has most number of weights, which means it is almost, okay, almost similar to what I did in case of the random forests. I just took a voted average. In case of random forest, I have taken a vote. In this case, I have converted that vote in the terms of this alpha m, which helped me calculate the weights, right? In both the cases, classification and regression, I'm going to calculate the weights in any case, right? I hope until this point in time it is clear. It is a new concept, so it will not be entirely clear. Maybe we can stop here for now. You can go through the video, then we are going to come back. So just to reiterate, we're going to set the weights 1 by n for each row, right? I, where the row number is going to be 1, 2, 3 until n. The initial value is set as 1 by n. And then for each model, m of I in the range of models, I create the basic model, I find the error of that model, then I calculate alpha of m. Using alpha of m, I'm going to update the weights for each and every row, right? Which is step number 1. And these are the internal steps A, B, C, and D. And then outside the step number 1 or outside the for loop, step number 2 is going to be normalize, right? Normalize each and every weight for all the rows R of I, right? And step number 3 is going to be construct the new tree. And this is going to continue. I'm going to continuously doing this. I'm going to continuously doing this. So this step number 1, this thing is going to be done for model M1, and then I'm going to get the new weights W1. Then I'm going to create a model M2. I'm going to create the new weights W2, and then I'm going to create using these weights the third model M3. I'm going to get the new weights W3 until and unless I have created the mth model. And by this time, my objective that my loss is very, very less, this should be done, right? So I'm going to stop at a certain stage where I'm no longer able to reduce the loss. Until this point in time, Rohit, any questions?
No questions as of now.
Okay, great. Then let's make it a stop here, because I think this is a complicated kind of a topic. Let's make a stop here. We're going to continue from tomorrow, where we can do some hands-on, and then we can look into the other types. So we have just looked into Adaboost algorithm, and then we will look into gradient boosting, because clearly there are some problems in Adaboost. As you can understand, we are still taking the voted average, right, by basis the weights, and then in case of regression, what we are doing, we are just taking the highest sum, right? This approximation may well go wrong in some cases, right? So the improvement is going to come into gradient boosting, and then further improvement is going to come into Xgboost, right? But the idea overall is going to be the same. We create one model, take some learning out of it, then we fit the next model, take some learning out of it, and then we are going to continue fitting it until m number of models. And we expect that by the end of this exercise, my objective of loss plus sigma, this should be met, and I should have a much, I mean, this is kind of a minimization problem. I should have a very, very small loss, right?
Sure, Bhavik.
Okay, Rohit, then let's continue from tomorrow.
Okay.
Thank you.
Thanks,
Bye.
Bhavik. Good night.